Mars has a volcano so large that if you stood at its base, you might not realize you were standing on a mountain at all. Olympus Mons rises about 22 kilometers, roughly 72,000 feet, above the Martian surface. Mount Everest reaches only about 8.8 kilometers, around 29,000 feet. Olympus Mons is nearly 3 times taller, but height is only part of what makes it strange. The volcano stretches roughly 600 kilometers, about 374 miles, across. Its base is so enormous that the curvature of Mars itself hides the summit from someone standing below. You could look toward the horizon in every direction and see what appears to be flat ground, and Olympus Mons is only one part of the story. Mars has an entire province of enormous volcanoes built over immense periods of time and large enough to deform the planet's crust. They grew to scales Earth could never easily reproduce, and their existence tells us that ancient Mars was not the frozen, lifeless world we see today. The strangest possibility is that some of this volcanic activity may have continued surprisingly recently. Scientists have found evidence suggesting that parts of Mars may have erupted within the last 50,000 years. In geological terms, that is almost nothing. Humans were already walking the earth. We had tools, fire, and the beginnings of organized societies. Mars may not have been finished with its fire, and that changes more than the history of volcanoes. Volcanic activity can reshape a planet's atmosphere, move water, create new minerals, and provide environments where chemistry can become surprisingly complex. If Mars once had life, its volcanoes may have helped create the conditions that allowed it to survive. So, how did a smaller planet build volcanoes larger than anything on Earth? Why did they grow to such extraordinary sizes? And if Mars really erupted within the last 50,000 years, how dead can we honestly call it? If space content like this is your thing, we've got plenty more. Subscribe and you'll have a new documentary waiting for you next time you need one. It starts with the volcano that makes every mountain on Earth look small. Mars becomes easier to understand when we stop treating it as a smaller Earth. Its gravity pulls with only about 38% of the strength you know here, changing how dust falls, how rocks travel, and how mountains can rise. Even a familiar landscape would behave differently under your feet. The air is the greater departure. Almost all of it is carbon dioxide, making the atmosphere less than 1% as dense as Earth's. A person standing there would face a pressure so low that exposed liquid water could not remain stable for long. The thin air also carries very little heat from one place to another, leaving the surface vulnerable to extraordinary temperature changes. Near the equator, an afternoon in summer can reach around 70 degrees Fahrenheit. At the poles during winter, temperatures can plunge toward minus 220 degrees. Between those extremes lies a world where warmth is temporary and intensely local. You can have sunlight overhead while the surrounding ground remains locked in deep cold. Mars also travels through space with two companions. Phobos is the larger and closer moon, an irregular body that circles the planet in less than 8 hours. Deimos is smaller and farther away, taking about 30 hours to complete its orbit. Their shapes and compositions have long supported the idea that both may have originated as captured asteroids, although their exact history remains under study. Look across the planet itself, and another division appears. The southern highlands rise above the younger northern plains, carrying immense numbers of ancient impact craters. The northern lowlands are smoother and lower, forming a planetary boundary known as the Martian dichotomy. Scientists still debate how this enormous difference formed, with possibilities ranging from colossal impacts to processes deep within the planet. Beneath those contrasting surfaces, Mars carries another record of its changing history. Its crust contains magnetic signatures preserved in ancient rocks, showing that the planet once possessed a global magnetic field. That field came from a dynamo, the movement of electrically conducting material inside the core. When that internal engine weakened, the protection it provided disappeared. Solar radiation and the solar wind could then interact directly with the upper atmosphere, helping remove gases over immense spans of time. The change was gradual, measured in hundreds of millions and billions of years, but its consequences reached the entire surface. Yet the Mars we see today is only one chapter. Early in its history, the planet held more atmospheric pressure, more surface water, and considerably more internal heat. Rivers crossed valleys, lakes occupied basins, and the crust was being reshaped by processes that had not yet slowed. So when we picture Mars beneath its dusty exterior, we are looking at a world whose present form conceals a much more active past. The cold plains and cratered highlands are the surviving surface of a planet that once had enough internal energy to transform itself on a planetary scale. Mars carries a swelling so immense that maps can make it look almost ordinary. Tharsis stretches roughly 2,400 miles across, rising about 6 miles above the surrounding terrain. Its footprint covers a vast portion of the Western Hemisphere, and beneath that surface lies one of the greatest concentrations of volcanic rock in the solar system. Imagine tracing its outline from orbit. You would find Olympus Mons standing to one side, while three enormous shields, Arsia Mons, Pavonis Mons, and Ascraeus Mons, form a long volcanic alignment nearby. Together with several smaller volcanic structures, they belong to a province containing about 12 major shield volcanoes. Their arrangement gives Tharsis a distinctive geometry, shaped by fractures and immense movements within the crust. The strange part is what happened to the planet beneath all that weight. Tharsis became such a tremendous load that it bent and depressed the surrounding crust, producing broad changes in Mars's topography and gravity field. You can see the signature from orbit. A deep regional trough surrounds portions of the rise, while distant areas were pushed upward in response. That redistribution of mass may also have influenced Mars's orientation through true polar wander, a process in which a planet's solid outer layers shift relative to its rotational axis. The idea matters because Tharsis was never simply sitting on Mars. Its growth became part of the planet's global structure. Lava continued spreading outward from the volcanic centers. Some flows traveled for enormous distances, filling low regions and burying older surfaces beneath successive layers of basalt. Over immense spans of time, eruption after eruption changed the elevation, texture, and shape of the surrounding plains. You can still follow those ancient pathways today. From spacecraft orbit, lava flows appear as broad overlapping sheets, channels, ridges, and hardened plains crossing terrain that existed before them. Each boundary marks a different episode in the construction of Tharsis, preserved because Mars lacks the vigorous surface recycling that constantly erases old landscapes on Earth. Then the crust began to respond in another direction. East of the Tharsis Rise, enormous fractures opened across the planet, forming the beginning of Valles Marineris. The canyon system eventually extended for roughly 2,500 miles, with some sections reaching more than 4 miles deep. At its widest, parts span hundreds of miles. You could place the continental United States across its length and still have room left on either side, but its importance is deeper than size. Valles Marineris records the mechanical consequences of building Tharsis beside a rigid planetary crust. As the region expanded and the surrounding rock adjusted, enormous blocks of crust fractured, dropped, and shifted. The result is a landscape where volcanoes and tectonic scars belong to the same geological story. Tharsis raised the surface, loaded the crust, redirected stresses, and helped transform an enormous region of Mars. What we see today is the frozen geometry of those forces, preserved across a planet that has spent billions of years keeping the record. A volcano on Earth rarely gets to stay in one place for long. The ground beneath it is moving, carried by a tectonic plate that slowly crosses the surface. Deep below, a hot spot can continue feeding magma upward, but the plate keeps drifting. New volcanic islands form over the heat, while older ones are carried away. Hawaii gives us a familiar example. The Hawaiian island chain records the movement of the Pacific plate across a long-lived hotspot. Each island marks a different position over the same source, creating a trail that grows older with distance. Mars works differently. Its outer crust does not behave as a collection of moving plates. Instead, the surface forms a largely continuous shell, allowing volcanic centers to remain over their sources for extraordinarily long periods. Imagine what happens when that movement disappears. Magma keeps rising through the same region, and each eruption adds another layer to the structure already there. Lava spreads outward, cools, and becomes part of the growing volcano. Then another eruption arrives, then another. Over hundreds of millions of years, repetition becomes architecture. That difference helps explain why Mars could produce structures on such an enormous scale. Earth distributes volcanic construction across moving plates, while Mars can concentrate it in fixed locations. The same deep heat source may continue building over one region until the volcano becomes hundreds of miles across. There is another advantage waiting beneath the surface. Mars has weaker gravity, only about 38% of Earth's. A volcanic mountain therefore experiences less downward force acting against its own mass. Its slopes can support greater heights before the accumulated rock begins to deform and spread. You can see the consequence in the shape of Martian volcanoes. They are broad shield volcanoes built from repeated flows that travel outward over gentle slopes. Their profiles rise gradually, allowing immense volumes of lava to accumulate without producing the steep, unstable forms common on many terrestrial volcanoes. Earth has its own giants. Mauna Loa in Hawaii is enormous, yet its growth is constrained by the moving crust beneath the Pacific Ocean. The volcano can expand for a long time, but its geological setting keeps changing around it. On Mars, the setting remains remarkably stable. The process does not require every eruption to be enormous. A relatively modest lava flow can become significant when multiplied across millions of eruptions and immense spans of time. Layers overlap, valleys disappear, older surfaces become buried. The volcano slowly occupies more of the landscape. This is why Olympus Mons reaches such extraordinary proportions. Its size reflects persistence more than violence. Mars gave one volcanic system something Earth rarely provides: a stationary foundation, weaker gravity, and geological time measured in hundreds of millions of years. Once you understand that combination, the giant volcanoes stop looking like impossible accidents. They become the natural architecture of a planet where the crust stayed in place long enough for fire beneath it to keep building. If you could walk across Olympus Mons, its greatest dimension would be difficult to recognize beneath you. The volcano spreads outward so gently that its immense bulk becomes a problem of scale rather than steepness. Its flanks rise at an average slope of only a few degrees, with broad surfaces extending for hundreds of miles. This shape tells us something about the lava that built it. Olympus Mons is a shield volcano, a structure formed mainly by repeated flows of relatively fluid basaltic lava. Instead of piling upward into a sharp cone, the lava traveled outward, covering enormous areas before cooling. Layer upon layer accumulated around the central vent. At the summit, the architecture changes abruptly. A vast caldera occupies the highest region, stretching roughly 53 miles across and reaching nearly 2 miles deep. Caldera means a volcanic depression formed when the ground above a drained magma reservoir collapses. Here, the summit contains 6 overlapping collapse structures, each preserving a separate episode in the volcano's long history. You can almost read those episodes from above. One collapse cuts into another, while younger surfaces partially cover older ones. The arrangement shows that Olympus Mons did not build itself during one prolonged eruption. Its activity arrived in pulses, separated by intervals when lava stopped reaching the surface. Around the lower boundary, the volcano develops another remarkable feature. A towering escarpment surrounds much of the base, rising several miles above the adjacent plains. This abrupt change in elevation marks the boundary between the enormous volcanic edifice and the terrain surrounding it. Beyond that boundary, the volcano's influence continues through a broad aureole of fractured and deformed terrain. Landslides, ridges, and layered deposits form a complicated ring around Olympus Mons, recording how its immense weight interacted with the crust over geological time. Higher up, altitude begins changing the atmosphere around the mountain. Air moving across the broad flanks is forced upward, where it expands and cools. Water vapor can then condense into clouds, creating recurring bands around the volcano. Spacecraft have photographed these cloud formations repeatedly, especially during the Martian afternoon. The summit rises so far above the surrounding surface that atmospheric conditions there differ sharply from those below. Pressure falls with altitude, and the already thin atmosphere becomes even more tenuous. From the summit, the planet's curved horizon would dominate the landscape. Orbital instruments can also detect differences that human eyes cannot. Infrared observations have revealed thermal variations across the caldera floor, showing that its surfaces formed at different times. Some areas retain distinct signatures from later resurfacing, while neighboring sections preserve older terrain. That makes Olympus Mons more than a giant mountain. Its shape, collapses, cliffs, clouds, and thermal patterns form a layered record of volcanic activity extending across an immense span of Martian history. 3 enormous volcanoes stand across Mars in a remarkably ordered line. Tharsis Mons, Pavonis Mons, and Ascraeus Mons rise northeast of Olympus Mons, forming the group planetary scientists call the Tharsis Montes. Their arrangement is too regular to dismiss as chance. Each volcano stretches for roughly 250 to 300 miles across. Their heights reach between 9 and 11 miles above the surrounding terrain. On Earth, any one would dominate the planetary landscape. Here, 3 such structures appear as parts of one immense volcanic province. Their alignment follows a major fracture zone in the Martian crust. These fractures are deep weaknesses where enormous stresses can open pathways through solid rock. Magma rising from the mantle could exploit those pathways, feeding volcanic centers along the same broad geological corridor. Tharsis Mons occupies the southern end of the chain. Its summit contains a caldera, roughly 72 miles across, creating a vast depression within the volcano. Inside that caldera, scientists have found evidence for an ancient glacial deposit, a layer of ice-related material preserved within the volcanic landscape. That discovery adds another dimension to Tharsis Mons, Ice and volcanism occupied the same place at different moments in Martian history. A volcano that once released molten rock could later become a landscape capable of preserving frozen deposits beneath the changing atmosphere. Farther north, Pavonis Mons sits almost directly across the Martian equator. Its summit caldera spans roughly 28 miles and reaches nearly 3 miles in depth. From above, its position gives the volcano a striking symmetry within the Tharsis region, while its broad flanks descend gradually into the surrounding terrain. Ascraeus Mons marks the northern end of the trio. It rises about 59,000 feet above the Martian reference level, making it the tallest of the three. Its immense shield extends across hundreds of miles, with lava flows preserving subtle differences between separate periods of construction. Then there is the spacing. Arsia Mons, Pavonis Mons, and Ascraeus Mons are separated by roughly 430 miles each, an unusually consistent pattern across such a vast landscape. For planetary geologists, that regularity provides a clue about what lies beneath them. A mantle plume is a column of unusually hot material rising from deep inside a planet. If that plume interacted with fractures within the crust, it could help explain why these volcanoes formed along one extended line rather than appearing randomly across Mars. We can therefore read the three volcanoes as more than isolated mountains. Their positions preserve information about deep structures that cannot be seen directly. The surface gives us the pattern, while the pattern points downward toward a mantle that once moved heat through Mars on a planetary scale. Today, the three shields remain fixed across the Martian landscape, separated by vast plains and connected only through their geological history. Their regular spacing is one of those rare details that lets us glimpse the hidden architecture beneath an entire world. For a moment, imagine Mars without its largest canyon. The planet would lose one of its most dramatic records of crustal movement. Valles Marineris cuts across the equatorial region for roughly 2,500 miles, forming a system of enormous troughs that can be seen clearly from orbit. Its origin reaches back to the growth of Tharsis. As volcanic activity raised and loaded that region, stresses spread through the surrounding crust. The Martian crust responded by stretching and fracturing, especially along zones already weakened by deep geological structures. Over immense spans of time, sections of the surface dropped between those fractures. This process is called rifting. A rift forms where crust is pulled apart, allowing blocks of rock to separate and sink. On Earth, we can watch similar processes creating valleys and eventually new ocean basins. On Mars, the process stopped before an ocean formed, leaving behind a colossal scar. Valles Marineris is far more complicated than one straight trench. Its western end begins near the Tharsis volcanic province, while its eastern reaches break into branching valleys and enclosed basins. Some chasms descend more than 4 miles below the surrounding terrain, while the widest sections stretch for hundreds of miles. If you stood beside one of these walls, the scale would be difficult to judge. Cliffs rise for miles, then disappear into shadowed depressions filled with landslide debris. Entire sections of the canyon floor are buried beneath material that once moved from the surrounding walls. Those landslides preserve another mystery. Some traveled for dozens of miles, spreading across the canyon floor with surprisingly low friction. Scientists have proposed several possibilities for what helped them move so far, including ice, water, or pressurized gases trapped beneath the surface. The evidence does not point to one simple mechanism. Mars has experienced changing temperatures, shifting groundwater, volcanic heating, and long periods of surface freezing. Each could have influenced the behavior of unstable slopes at different times. Some landslide deposits are enormous enough to cover hundreds of square miles. Their surfaces retain ridges and flow patterns that reveal how the debris traveled, accelerated, and eventually came to rest. Even the canyon's name carries a human connection. Valles Marineris was named for the Mariner 9 spacecraft, which reached Mars in 1971 and became the first spacecraft to orbit another planet. Its images revealed the immense canyon system in unprecedented detail. Today, when Mars approaches opposition, portions of its surface can be glimpsed through powerful amateur telescopes. The canyon itself is too large to resolve as a detailed landscape from Earth, yet its presence contributes to the dark markings observers can trace across the planet. What looks distant through a telescope is therefore a structure formed by immense forces beneath the surface. Valles Marineris records the moment when Mars's crust could no longer accommodate the stresses imposed across its volcanic heart. Long before Mars became the cold world we recognize, its interior carried enough heat to reshape the surface repeatedly. During the Noachian period, more than 4 billion years ago, volcanic activity was widespread, releasing gases from deep within the planet and changing the atmosphere above it. Each eruption delivered more than molten rock. Volcanoes released carbon dioxide, sulfur dioxide, and water vapor, adding gases that could interact with the young atmosphere. Carbon dioxide helped provide greenhouse warming, while volcanic water contributed to a climate in which liquid water could exist under favorable conditions. The evidence for that ancient water remains spread across the landscape. Valleys branch through cratered terrain. Ancient lake basins preserve sedimentary deposits. At Jezero Crater, the Perseverance rover has been examining an old delta where a river once entered a standing body of water. Those environments did not require a permanently warm Mars. Climate models allow for changing conditions, with volcanic gases potentially contributing to temporary periods when temperatures and atmospheric pressure became more favorable for surface water. The planet may have moved through repeated intervals of activity and decline, with volcanic pulses helping reshape the atmosphere between colder phases. These changes would have varied across regions and through time. Sulfur dioxide added another layer to the story. In the atmosphere, volcanic sulfur could react with water vapor and produce sulfuric acid aerosols. These particles can reflect sunlight and cause temporary cooling after major eruptions. Over longer periods, however, volcanic carbon dioxide could contribute to warming. Mars therefore had a complicated atmospheric response to its volcanoes. An eruption could alter temperatures in opposing ways, depending on the gases released and how long they remained in the atmosphere. You can think of the volcanic system as part of a planetary exchange, moving material from the interior into the sky and eventually back onto the surface. As the planet's internal heat gradually diminished, volcanic activity became less widespread. With fewer eruptions replenishing the atmosphere, gases were increasingly lost through escape processes and chemical reactions at the surface. Water followed several paths. Some escaped to space, while much of what remained became trapped as ice beneath or within the ground. The landscape preserves the transition. Younger surfaces carry fewer signs of sustained volcanic renewal, while ancient regions retain the scars and deposits of a far more active Mars. Every buried flow and altered mineral adds another piece to the timeline. We can still trace that ancient world through rocks and terrain. The channels, deltas, and lake deposits are remnants of a planet whose atmosphere once behaved very differently. For a span of geological time, fire beneath Mars helped maintain the conditions above it. Then that internal engine weakened, and the balance changed. Beneath the surface of Mars, some volcanic landscapes may continue farther than the eye can follow. When a lava flow moves across the ground, its exposed surface cools first, forming a hardened roof, while molten material continues flowing underneath. Eventually, the interior can drain away. What remains is a long, hollow passage, preserved within the solidified lava. These structures are called lava tubes, and Mars may contain versions far larger than those familiar on Earth. Lower gravity allows lava to spread differently, while enormous eruptions can produce flows covering immense areas. Some Martian lava tubes could reach hundreds of feet across and extend for many miles beneath the surface. Their true dimensions remain uncertain because we have never entered one. From orbit, however, we can sometimes see where these underground structures have collapsed. High-resolution images from the Mars Reconnaissance Orbiter reveal circular pits scattered across volcanic regions, including areas surrounding Olympus Mons. Each opening may mark a section where the roof could no longer support its own weight. The geometry is important. A chain of collapse pits can trace the hidden path of a lava tube, allowing scientists to infer underground structures from features visible above. These spaces could also change how we think about survival on Mars. The surface receives intense radiation from space, while temperatures can shift dramatically between day and night. A buried cavity would provide shielding from both hazards, creating a naturally protected environment beneath layers of rock. Some lava tubes may also preserve materials that disappeared from the exposed surface. Ice could remain stable in protected regions, while ancient mineral deposits might retain chemical evidence from periods when water interacted with volcanic heat. Those environments are especially interesting to scientists searching for signs of past habitability. The possibility of human use adds another dimension. Building a habitat on the surface would require thick shielding, pressure containment, thermal control, and substantial structural support. An existing lava tube could provide much of the surrounding rock naturally, reducing the amount of material future explorers would need to construct. You can imagine a settlement beneath Mars, with equipment and living spaces arranged inside an ancient passage formed by flowing lava. Sunlight would enter only through engineered openings or surface structures, while the surrounding rock would provide protection overhead. Some collapse pits are remarkably large. Individual openings can span hundreds of feet, yet the visible opening may represent only a small part of what lies below. The deeper significance is geological. Lava tubes are frozen evidence of movement that happened beneath an ancient surface. They preserve the pathways followed by molten rock after the outer landscape had already begun to harden. Mars may therefore contain a second landscape beneath the one we can see, shaped by rivers of lava that disappeared millions of years ago. The surface records where they broke through. Underground, their abandoned channels may still preserve the architecture of that vanished world. Some of the largest channels on Mars begin with an event that happened beneath the ground. There, water stored in fractures and porous rock could remain frozen or trapped under pressure for immense periods. Then heat arrived. A volcanic intrusion is molten rock forcing its way through the crust without necessarily reaching the surface. When such magma entered ice-rich ground, the surrounding material could warm rapidly. Ice melted, groundwater expanded, and pressure began building within sealed underground spaces. Eventually, the crust could no longer contain it. Water burst outward, carrying enormous quantities of sediment and rock across the surface. Instead of slowly carving a valley over thousands of years, these floods could reshape entire regions during comparatively brief episodes. You can see their paths today. Mars contains outflow channels tens of miles wide, with streamlined islands, scoured floors, and enormous terraces that preserve the direction of ancient currents. Some channels extend for hundreds of miles across the northern lowlands. Their scale is difficult to compare with anything on modern Earth. Estimates of discharge for the largest Martian floods reach extraordinary values, far exceeding the flow of Earth's greatest rivers. Water moved with enough force to excavate bedrock, transport boulders, and strip entire surfaces down to deeper layers. The source of that water was probably not a single underground reservoir. Mars may have contained interconnected aquifers, pockets of groundwater, and ice deposits distributed through the crust. Volcanic heat could have activated different regions at different times, producing separate flooding episodes across geological history. This relationship becomes especially interesting around Tharsis. The volcanic province was built through repeated intrusion and eruption, injecting heat into surrounding rock while fracturing the crust. Those fractures could provide pathways for both magma and groundwater, allowing the two systems to interact below the surface. Once pressure broke through, the escaping water could spread rapidly across low-lying terrain. Temporary lakes may have formed where floodwaters encountered broad basins, while sediment settled into layers that later became geological records of the event. Some researchers have proposed that volcanic heating may have helped trigger specific outflow events, although the exact mechanisms remain an active area of study. Other floods may have resulted from pressure changes, crustal deformation, or melting caused by geothermal heat without a direct volcanic eruption. What matters is the connection between processes that seem separate from orbit. Fire beneath Mars could mobilize water hidden within the crust, and that water could then transform the surface above it. The channels remain after the water is gone. Their shapes preserve the speed, direction, and immense force of floods that no human witnessed. Across Mars, ancient volcanic heat and underground water once met beneath the crust, and when that balance failed, an entire landscape could move. A compass would have told a very different story on ancient Mars. Somewhere beneath the southern highlands, rocks still preserve the direction of a magnetic field that vanished billions of years ago. Their minerals became aligned as molten material cooled, locking a faint record into the crust. That magnetism is more than a geological curiosity. It points toward an engine that once operated deep inside Mars. A planetary dynamo forms when electrically conducting material moves within a planet's core, generating a global magnetic field. Earth still has one. Mars once did too. The surviving magnetic patterns are strongest across portions of the ancient southern crust. They appear in broad bands, with neighboring regions sometimes recording different magnetic orientations. Such patterns are difficult to explain without a field that existed while those rocks were forming. Then the engine weakened. Mars is smaller than Earth, so its interior lost heat more efficiently over geological time. As the core evolved, convection within its electrically conducting material became insufficient to sustain the dynamo. The global field faded, leaving the crust with its ancient magnetic record but little planetary protection. For the atmosphere, that change mattered enormously. The magnetic field had acted as a shield against the solar wind, a continuous stream of charged particles flowing outward from the sunday. Without that protection, the upper atmosphere became increasingly exposed. The loss was gradual. Individual particles escaping into space would barely matter on human timescales, yet repeated over hundreds of millions of years, the effect could become planetary. Lighter atmospheric components were especially vulnerable, while ultraviolet radiation helped break apart molecules high above the surface. Mars therefore entered a long atmospheric decline. The pressure dropped, surface water became increasingly unstable, and the environment changed along with it. The geological record suggests that this transformation unfolded alongside the cooling of the planet's interior. But there is an intriguing possibility involving the volcanoes themselves. The enormous volcanic province of Tharsis developed during the same broad era when Mars was losing its early internal heat. Scientists have considered whether such concentrated volcanic activity altered the way heat moved through the mantle, potentially affecting the thermal evolution of the core. The connection remains unresolved. Volcanism could have influenced internal heat flow, or both volcanic activity and the weakening dynamo could simply reflect the same deeper process, the gradual cooling of a young planet. That distinction matters because the sequence would change how we understand Mars's transformation. If volcanic construction helped alter the planet's internal heat balance, then the forces that built its greatest mountains may have contributed indirectly to the loss of its magnetic protection. We cannot yet assign a simple cause and effect. What we can see is a remarkable chain preserved across the planet, ancient rocks recording a vanished magnetic field, an atmosphere gradually escaping, and volcanic systems rising while Mars's interior cooled. The surface remembers what the planet itself can no longer produce. Age on Mars can be measured by counting scars. Every impact crater left across a lava plain becomes a mark on the surface, and the longer that ground remains exposed, the more scars accumulate. This method, called crater counting, gives planetary scientists a way to estimate when a surface formed. We compare the number and size of craters against established impact rates, then calculate a probable age. Fewer craters generally indicate younger terrain. In the Cerberus Fosse region of Elysium Planitia, the results are striking. Some lava flows appear to have formed only a few million years ago, with estimates reaching roughly 2.5 million years. On a planet whose volcanic history stretches across billions of years, that is remarkably recent. The landscape itself preserves the evidence. Long fissures cut across the plains, marking fractures where magma once reached the surface. Lava spread outward from these openings, covering older terrain with dark volcanic material before cooling into solid rock. Then researchers found something even younger. In 2020, David Horvath and his colleagues reported evidence for a peculiar deposit surrounding part of the Cerberus Fosse system. Their study was later published in the journal Icarus. The material appeared unusually dark and thermally distinctive, with mineral characteristics consistent with volcanic debris. Crater counting produced an estimated age between roughly 53,000 and 210,000 years. That range is broader than a single date, but even its older boundary places the deposit astonishingly close to the present. Imagine the timeline for a moment. When this material may have erupted, humans were already living on Earth. Our ancestors were making tools, moving across continents, and adapting to changing climates. On Mars, a fissure may have opened and scattered volcanic material across the surrounding plain. The deposit may represent explosive activity rather than an ordinary lava flow. Researchers proposed that it could be a pyroclastic deposit formed when volcanic material was violently fragmented and distributed around the fissure. The interpretation remains uncertain because no rover has collected a sample from the site. That uncertainty matters. A young volcanic surface does not automatically prove that Mars is erupting today. Crater dating carries uncertainties, and the deposit's volcanic origin itself remains an interpretation rather than a directly sampled fact. Still, the evidence changes the question. If volcanic activity occurred tens of thousands of years ago, Mars cannot be treated as a world whose interior stopped moving in the distant past. Some heat remained beneath the crust long after the great volcanoes had finished building their enormous structures. The Cerberus Fossae region is therefore unusual for another reason. It sits within a landscape where young lava, fractures, and seismic activity occur together, giving scientists several independent clues about recent geological processes. We are left with a planet whose youngest volcanic traces may belong to an era when human history had already begun. The material remains frozen on the surface, preserving a possibility that Mars's interior may have remained active far longer than its barren appearance suggests. For years, Mars had been imagined as a world whose interior had largely gone still. Then a small instrument began recording its movements from the surface. The InSight lander arrived in November 2018, carrying a seismometer built to detect vibrations traveling through the planet. Each signal offered a different kind of measurement because seismic waves can pass through layers we cannot see. They reveal changes in density, temperature, and structure deep beneath the ground. Between 2019 and 2022, InSight detected more than 1,300 seismic events. Most were small. Some were barely more than tremors. Yet their distribution revealed something important about where Mars remains mechanically active. A surprising number originated near Cerberus Fossae, where fractures cut across the plains and some of the youngest volcanic deposits are found. The connection is intriguing because earthquakes and recent volcanism can both reflect stresses moving through the crust. Still, the evidence does not establish that magma caused those particular events. Then came larger disturbances. In 2021, InSight recorded a magnitude 5 Marsquake. Another event of similar strength followed in 2022. For a planet that has lost much of its internal activity, these disturbances provided unusually strong signals from beneath the surface. Their origins remain uncertain, and the distinction matters because several processes can produce similar seismic signatures. One possibility is thermal contraction, as the crust gradually cools and shrinks. Another involves tectonic stress accumulating along ancient fractures. Volcanic processes remain under consideration, although direct evidence linking the quakes to active magma has not been established. The seismic waves also changed our understanding of Mars itself. By tracing how those waves traveled through the planet, scientists could estimate the size and composition of its core. The results indicate a larger, lighter core than many earlier models had predicted, with substantial amounts of lighter elements mixed into the molten metal. That finding reaches deeper than any surface photograph. When you hear a Marsquake, you are hearing the planet reveal its interior indirectly. A tremor begins somewhere beneath the ground, travels through hidden layers, and eventually reaches an instrument waiting millions of miles away from Earth. InSight also showed that the mantle behaves differently from some previous models. Heat moves through the interior in ways that affect how the crust stretches, fractures, and responds to stress. The planet's geological history is therefore written not only across its surface, but through vibrations passing beneath it. Mars still has an active interior in the broad geological sense. Its core remains molten, its crust continues to deform, and seismic energy still travels through its depths. The planet may have lost the vigor of its youth, yet its interior has never completely stopped speaking. On Earth, volcanoes are measured against landscapes we can recognize. Mauna Loa rises from Hawaii as the largest volcano by volume on our planet, containing roughly 19,000 cubic miles of volcanic rock. Olympus Mons belongs to another scale entirely. Estimates place its total volcanic volume near 1.2 million cubic miles, enough material to equal more than 60 Mauna Loas. Imagine taking one of Earth's greatest volcanoes and repeating it again and again until the count passes 60. Even that comparison begins to lose meaning. The difference comes partly from how the two planets build volcanoes. Earth's crust moves over its interior, spreading volcanic activity across different locations. Mars kept its crust largely fixed, while magma repeatedly reached the same region. Over immense spans of time, layer after layer accumulated. Olympus Mons, therefore, became a single volcanic structure of extraordinary volume. Its broad foundation spreads across thousands of square miles, while repeated lava flows gradually added new material to the surface. Each individual eruption could seem modest against the finished mountain. Together, they created something planetary in scale. Now place that volume beside Earth's most powerful volcanic systems. Yellowstone is a vast volcanic region beneath North America, known for enormous eruptions separated by hundreds of thousands of years. Its Huckleberry Ridge eruption occurred about 2.1 million years ago and released roughly 600 cubic miles of volcanic material. Olympus Mons contains around 2,000 times that volume. The comparison requires care. Yellowstone and Olympus Mons formed through very different volcanic processes, so their volumes do not represent the same kind of eruption. Yellowstone's major events were explosive, while Olympus Mons grew primarily through successive outpourings of fluid lava. That distinction makes the numbers more useful, not less. One system releases immense amounts of material in comparatively brief episodes. The other accumulates its mass gradually across geological ages. We are comparing two different ways a planet can move heat from its interior toward the surface. Earth's volcanic record contains eruptions capable of reshaping entire regions. Mars produced a structure whose accumulated mass reaches far beyond those familiar terrestrial examples. There is no need to imagine one enormous eruption creating Olympus Mons in a single event. Time did the work. For us, a million years is almost impossible to picture. Geological time makes repeated eruption after repeated eruption seem almost like a continuous process, even though enormous intervals could separate individual events. That is where Olympus Mons becomes more than a record holder. Its size preserves evidence of how planetary interiors behave when the crust remains fixed over a persistent source of heat. Earth rarely allows a volcano such a stable foundation. Mars did, and across immense stretches of time, that difference transformed volcanic activity into a mountain beyond any terrestrial equivalent. At the foot of Olympus Mons, the landscape changes abruptly. The broad volcanic slopes give way to a towering escarpment, a steep geological boundary surrounding much of the volcano's base. In places, this wall rises nearly 4 miles above the plains. It is an immense change in elevation, yet the summit remains far beyond the horizon. Standing there, you would be beside one of the largest exposed cliffs known on Mars. The escarpment formed through the immense stresses created by Olympus Mons itself. As the volcano accumulated layer after layer of lava, its enormous weight pressed downward on the crust beneath it. Around the margins, that pressure forced the surrounding rock to deform, producing a sharp transition between the elevated volcano and the lower plains. But the boundary is more complicated than a single vertical wall. Beyond the escarpment lies a vast terrain called the Oriole. This region contains enormous blocks, ridges, and fractured ground arranged around the volcano's outer edge. Some researchers interpret these structures as remnants of material that slumped outward as the volcano grew, while others emphasize crustal deformation and gravitational collapse. The Oriole stretches hundreds of miles from Olympus Mons. Its scattered formations can resemble detached islands around the main volcanic structure, although they are connected to the volcano through a much larger geological history. For us, this surrounding terrain provides an unusual way to understand the volcano's weight. The mountain did not simply rise above Mars. Its mass altered the crust around it, leaving deformation far beyond the slopes we would normally consider part of a mountain. Closer to the escarpment, exposed rock preserves another record. Layers appear across portions of the walls, revealing successive episodes of lava emplacement. Each flow cooled into rock before later eruptions buried it beneath another layer. The result is a geological archive. Instead of pages, there are terraces and exposed surfaces. Instead of ink, there are minerals preserved from different volcanic episodes. By studying their composition and relationships, planetary scientists can reconstruct changes in the volcano's activity across immense spans of time. Some portions of the escarpment also contain landslide deposits, where sections of the volcanic margin collapsed and moved outward. Mars's lower gravity allowed these enormous masses to travel across the surrounding terrain, leaving broad deposits that remain visible from orbit. The scale becomes especially difficult to appreciate from above. An escarpment that appears as a narrow boundary on a planetary map can represent a wall extending for hundreds of miles across the surface. You could stand beneath it and see only one section. The rest would continue beyond the horizon, following the immense curve of Olympus Mons. Above that boundary, thousands of feet of volcanic rock rise gradually toward the summit, while beneath your feet, the crust carries the imprint of a mountain whose weight reshaped everything around it. Every afternoon on Mars, the atmosphere responds to the mountains below it. Around the Tharsis volcanoes, rising air can create clouds that return with remarkable regularity. Water ice clouds gather along the flanks of Olympus Mons and the Tharsis Montes as moist air climbs the enormous slopes. Higher elevations bring lower temperatures, allowing water vapor to freeze into tiny crystals suspended within the atmosphere. The process is familiar in principle. We see something similar around mountains on Earth, where rising air cools and produces clouds. On Mars, the same basic physics unfolds across a far thinner atmosphere and a much colder world. Around Olympus Mons, these clouds can stretch across enormous distances. Orbital cameras have photographed them repeatedly, revealing patterns that change with the planet's seasons and daily cycle. Their appearance provides scientists with another way to study atmospheric circulation around the largest volcanic structures. You can think of the volcanoes as obstacles placed directly into the Martian atmosphere. Winds encounter their immense slopes, rise around their sides, and change direction as the terrain forces the air into new paths. The effect extends beyond individual clouds. Tharsis also influences the movement of dust, one of the most important materials in the Martian atmosphere. Fine particles can be lifted from the surface and carried across great distances by winds, sometimes remaining suspended for extended periods. Most dust storms remain regional. Occasionally, however, conditions allow one to expand dramatically. In 2018, a dust storm developed into a planet-wide event. Within weeks, dust had spread around Mars, obscuring much of the surface from view. The storm persisted for months and transformed the amount of sunlight reaching the ground. That mattered enormously for the Opportunity rover. Opportunity depended on solar panels to generate electrical power. As the dust thickened overhead, sunlight became increasingly difficult to collect. Eventually, communication with the rover was lost, ending a mission that had already operated for many years, beyond its original planned lifetime. The storm revealed something unusual about Mars. Its atmosphere may be thin, yet it can still move enough dust to reshape conditions across an entire planet. Volcanoes influence that circulation through their immense topography. Their slopes redirect winds, alter cloud formation, and help organize atmospheric movement across the Tharsis region. Even the clouds themselves become useful scientific markers. By tracking when they appear, where they form, and how they move, researchers can study wind patterns that are otherwise difficult to observe directly. There is also a seasonal rhythm to this activity. As Mars travels around the Sun, temperatures and atmospheric conditions change, shifting the balance between water vapor, ice clouds, and airborne dust. So the volcanoes remain connected to the atmosphere long after their major eruptions ended. Their rock still controls the movement of air above it, turning ancient geological structures into active participants in Martian weather. The surface may preserve the planet's volcanic history, but the atmosphere continues to trace those mountains every day. At the summit of Olympus Mons, the ground records a cycle of destruction and renewal. 6 enormous collapse depressions overlap across the summit, each marking a separate stage in the volcano's long history. These structures are calderas, broad depressions formed when a magma chamber beneath a volcano loses enough support for its roof to collapse. An eruption can remove molten rock rapidly, while underground movement can drain a chamber without producing a single, spectacular surface event. Olympus Mons preserves this process 6 times. Each caldera overlaps parts of the others, revealing that the summit was reshaped repeatedly. One collapse occurred, the volcano continued evolving, and later eruptions altered the same region. Eventually, another chamber emptied, producing another depression across the older terrain. The arrangement gives us something more valuable than a dramatic summit feature. It provides evidence that Olympus Mons developed through pulses of volcanic activity rather than one uninterrupted episode. Those pulses may have been separated by enormous spans of time. Mars measures geological change differently from a human lifetime, and a period lasting millions of years can represent only one chapter in the volcano's development. Tharsis Montes offers another remarkable example. Its caldera stretches roughly 72 miles across and reaches nearly 2 miles in depth, making it the largest summit caldera among the major Tharsis volcanoes. Within a depression, that vast atmospheric circulation can behave differently from the surrounding slopes. Air moving across the volcano encounters changes in elevation, temperature, and pressure, allowing local cloud patterns to develop within and around the caldera. Volcanoes Mons and Snoozy Mons preserve their own collapse structures as well. Their summit floors contain fractures and smaller depressions, signs that the volcanic system continued changing after the major collapse events. Some areas also appear to have been resurfaced by later lava. Fresh volcanic material covered portions of older terrain, partially burying earlier structures beneath new rock. That creates a layered history. A fracture may cut across one surface, while another lava flow covers it. A later collapse may then disturb that younger layer, leaving several generations of geological evidence visible together. For planetary scientists, these relationships reveal the sequence of events without requiring a human observer to have witnessed them. The rock itself preserves the order. You can almost read the summit as a timeline. Each overlapping depression represents a moment when the balance beneath the volcano changed. Magma accumulated, moved, erupted, or drained away. The roof above it responded, and the surface recorded the change. Calderas therefore tell us something about the hidden plumbing of a volcano. Their shapes, fractures, and relative ages provide clues about where magma traveled and how volcanic pressure changed through time. Olympus Mons was repeatedly rebuilt around these collapses. Its summit was reshaped again and again, while enormous volumes of lava accumulated across the surrounding slopes. The result is a volcano whose surface contains evidence of repeated internal adjustment. Its calderas remain visible because Mars preserved those ancient changes, leaving the summit marked by successive episodes of collapse and renewal. The surface of Elysium Planitia carries a different kind of volcanic story. Here, the scale is smaller, yet the evidence reaches much closer to the present than the ancient landscapes surrounding it. Far from the immense Tharsis volcanoes, Elysium forms Mars' second major volcanic province. Three principal volcanoes rise from this region: Elysium Mons, Hecate's Tholis, and Albor Tholis. Elysium Mons reaches roughly 29,000 feet above the surrounding plains, placing it among the planet's more substantial volcanic edifices. Its importance, however, comes from age rather than size. Elysium Planitia contains some of the youngest volcanic deposits identified anywhere on Mars, giving planetary scientists a rare opportunity to study activity that occurred remarkably late in the planet's geological history. In 2020, researchers reported a volcanic deposit estimated to be about 50,000 years old. The material forms a dark sheet covering roughly 15 square miles, spreading across terrain that had already existed for immense spans of time. 50,000 years is almost unimaginably brief on a planetary clock. On Earth, humans were already living during that interval. Our ancestors were using fire, shaping tools, and moving through landscapes beneath a changing sky, while Mars was still capable of producing fresh volcanic rock. That comparison gives the deposit unusual significance. We often picture Mars as a world whose geological story ended long ago, leaving only erosion and dust to reshape its surface. Elysium offers a more complicated record. Crater counting provides one method for estimating the age of such surfaces. A newly exposed lava flow begins with very few impact craters, while older terrain gradually accumulates more. By comparing crater populations across surfaces, scientists can estimate when volcanic material was emplaced. The result is not an exact timestamp. It is a geological estimate built from known impact rates and careful comparisons. Even with that uncertainty, the Elysium deposit remains exceptionally young. Then there is the seismic record. The InSight lander operated from Elysium Planitia, placing a sensitive seismometer directly within this unusual volcanic province. Between 2019 and 2022, it detected more than 1,300 seismic events across Mars, many associated with the surrounding region. That connection matters because surface geology and interior movement can reveal different parts of the same system. Young lava suggests relatively recent heat reaching the surface, while Marsquakes show that stresses continue moving through the crust beneath it. Elysium, therefore, gives us a rare overlap of evidence. Volcanic deposits mark recent changes at the surface, and seismic activity reveals movement below. For you, the strange part is the timescale. A planet can appear unchanged from orbit, yet its interior may still be adjusting beneath the dust. Elysium Planitia preserves both traces, giving Mars a geological present that is far more complicated than its barren appearance suggests. An eruption on Mars would begin under a sky unlike anything above a terrestrial volcano. The atmosphere is less than 1% as dense as Earth's, changing the behavior of ash, gas, and molten rock from the first moments. Here, an eruption column could rise rapidly before spreading outward. On Earth, Thick air helps shape towering plumes, while pressure and turbulence influence how volcanic material travels. Mars offers far less resistance, allowing fine particles and gases to climb to extraordinary heights before gravity and atmospheric currents disperse them. Estimates suggest a powerful Martian eruption could send material 20 to 30 miles above the surface. Some of Earth's largest eruptions have produced columns reaching roughly 12 to 15 miles. The difference would become visible in the shape and reach of the plume, with material expanding through an atmosphere too thin to hold it in familiar forms. Gravity changes the scene again. Mars has only about 3/8 of Earth's surface gravity, so rocks launched from a volcanic vent could remain airborne longer and travel much farther before returning. Larger fragments might land many miles from their source, spreading fresh material across terrain that had remained exposed for ages. Lava would behave differently as well. With weaker gravity and a sparse atmosphere, a flowing lava sheet could cover broad distances before cooling into solid rock. Its movement would depend on temperature, composition, slope, eruption rate, and the properties of the surrounding ground. You could watch a new landscape being assembled across an already ancient one. Water would introduce another possibility. Mars lacks the abundant groundwater that fuels many explosive volcanic interactions on Earth, where magma meets liquid water and rapidly generates expanding steam. Yet buried ice could still exist beneath the surface in suitable regions, creating conditions for explosive interactions if rising magma reached it. Such an encounter could produce a very different eruption style. Rapid heating would transform ice into vapor, expanding violently and fragmenting surrounding rock. The resulting blast could excavate the surface while distributing volcanic debris across a wide area. Even the ash would behave strangely. Fine particles could remain suspended for extended periods, while winds carried them across enormous distances. Electrically charged dust and ash might also interact with the atmosphere, producing unusual atmospheric effects around the eruption. For us, the most remarkable part would be the absence of familiar boundaries. There would be no dense atmospheric ceiling shaping the plume, no nearby forests or oceans responding to falling ash, and no cities waiting beneath the horizon. A Martian eruption would reveal a planet still capable of changing itself. For a brief geological moment, ancient volcanic forces would become visible again, rising from beneath a world whose surface has preserved their history for billions of years. Ancient Mars may have experienced a climate rhythm written into the eruptions of its volcanoes. Each major outburst could alter the atmosphere, changing how much sunlight reached the surface and how much heat remained trapped near the ground. Sulfur dioxide was among the important gases released by enormous Martian eruptions. Once airborne, it could react with atmospheric moisture and form sulfuric acid aerosols, tiny droplets capable of reflecting incoming sunlight. For a time, that process could cool the planet. The effect would have resembled volcanic cooling observed on Earth. After especially large eruptions, sunlight reaching the ground could decrease, lowering surface temperatures before atmospheric chemistry shifted again. Then the longer-lived warming influence of volcanic greenhouse gases could become more important. Carbon dioxide played a major role in that longer process. Released from magma and volcanic vents, it could accumulate in an atmosphere that was once substantially thicker than the one surrounding Mars today. Water vapor added another greenhouse influence, allowing the atmosphere to retain more heat under the right conditions. The result may have been a planet whose climate changed in pulses. A period of volcanic cooling could be followed by warming, with each transition altering where water could exist and how long it remained active on the surface. That possibility matters because Mars preserves enormous networks of valleys and ancient lake basins. Their existence requires episodes when water moved across terrain that is now dry. Volcanic gases offer one mechanism for creating those temporary environmental windows. We should be careful with the word livable. Scientists do not know that every volcanic episode produced warm conditions, and climate models disagree about how effectively greenhouse gases could overcome the cooling effects of aerosols. The chemistry depends on eruption size, atmospheric pressure, dust, water availability, and the composition of the volcanic emissions. Still, the timing is intriguing. Tharsis formed over immense spans of geological time, while evidence for surface water is concentrated in ancient periods when Mars appears to have possessed a thicker atmosphere. Volcanism therefore belongs in the discussion of why those wetter intervals occurred when they did. Some researchers have explored scenarios in which individual eruptions helped trigger relatively warm periods lasting thousands of years. That may sound brief against geological timescales, yet thousands of years can provide ample opportunity for rivers to cut channels, lakes to fill basins, and minerals to record interactions with water. Imagine the atmosphere responding to a distant eruption. First, reflective aerosols spread through the sky. Surface temperatures shift. Later, greenhouse gases exert their influence, and the balance changes again. For you, the remarkable idea is that Mars' ancient climate may have been paced by events deep beneath its crust. Volcanoes could have altered the atmosphere, while the atmosphere determined where water could persist. The planet's volcanic history may therefore be more than a record of changing landscapes. It may also preserve the rhythm of ancient climate itself, with eruptions helping determine when Mars briefly became wetter, warmer, and more favorable to surface water. From orbit, Mars reveals another layer of its volcanic history whenever we look closely enough. The Mars Reconnaissance Orbiter has been circling the planet since 2006, turning distant volcanic landscapes into detailed geological records. Its most powerful camera, the high-resolution imaging science experiment, can resolve surface features roughly 3 feet across. At that scale, a broad lava plain becomes something much more intricate, with overlapping flows, fractured ground, ridges, pits, and subtle changes in texture. Across Tharsis, these details have changed how scientists read volcanic terrain. Individual lava flows can be separated from one another, even when their boundaries are faint from greater distances. Differences in surface texture can reveal which flows formed earlier, which ones covered them later, and where volcanic activity returned after long intervals. The camera has also exposed the structure of collapse features. Circular pits and elongated fractures appear across regions shaped by ancient volcanic forces, giving scientists clues about what happened beneath the surface. Some openings mark places where underground cavities collapsed, while others trace weaknesses created as enormous volumes of lava moved through the crust. Then there is the chemistry. The Mars Reconnaissance Orbiter carries the Compact Reconnaissance Imaging Spectrometer for Mars, an instrument designed to identify minerals by the wavelengths of light they absorb. Instead of simply seeing the ground, it allows scientists to determine what the ground is made of. That distinction matters. Volcanic rocks change as they interact with the Martian environment, gradually developing different mineral signatures through weathering and alteration. Fresh basaltic lava contains minerals such as olivine and pyroxene, and their spectral signatures can help distinguish relatively young volcanic surfaces from terrain exposed for much longer periods. Across Tharsis and Elysium, mineral maps have therefore added another dimension to the geological story. A lava flow can have a particular shape, texture, and mineral composition allowing researchers to compare evidence that comes from completely different physical processes. You can think of it as reading several records at once. One layer comes from the shape of the terrain, another comes from its surface texture, a third comes from the minerals themselves. But orbital observation has revealed something even more fundamental. Mars contains far more small volcanic structures than earlier surveys could identify. Dozens of previously uncatalogued vents, small shield volcanoes, and lava flow fields have emerged from newer imagery. Many were simply too subtle or too small for older cameras to distinguish from the surrounding landscape. Each discovery changes the inventory slightly. A vent appears here, a buried flow emerges there, and a fracture reveals another connection between surface structures. After decades of orbital observation, the catalog remains incomplete. That is a remarkable position for planetary science. We have mapped an entire world, yet the volcanic record continues to expand whenever our instruments resolve another level of detail. Mars has been surveyed from orbit for years, and still, beneath every broader pattern, smaller traces are waiting to be recognized. Jezero crater preserves a sequence written into its rocks, and the Perseverance rover has been reading that sequence from the ground. When the rover arrived in February 2021, scientists already knew the crater contained an ancient river delta, making it an important place to investigate the history of Martian water. The deeper surprise came from beneath the sediment. Instead of finding a crater floor composed entirely of deposited material, Perseverance encountered igneous rocks, formed when molten rock cooled and hardened. These rocks changed the geological story of Jezero. Among them were olivine-bearing igneous rocks, containing a mineral that commonly forms within cooling magma. Their origin could involve an ancient lava flow or a larger body of magma that cooled beneath the surface. Either way, the crater floor preserves evidence of volcanic processes that happened before the waters associated with Jezero's river system arrived. That order matters. We can separate the history into distinct stages. Volcanic material formed the foundation, water later moved across the region, sediments accumulated, and eventually the surface became the dry landscape we see today. Perseverance can investigate this sequence directly. Its instruments examine the chemistry, texture, and mineral composition of individual rocks, allowing scientists to connect what they see on the ground with observations made from orbit. Each measurement narrows the range of possible histories, while revealing how the crater floor changed before the river arrived. The igneous rocks are especially valuable for establishing time. Sedimentary rocks often record environments and events without providing an equally precise date for when the material originally formed. Certain igneous minerals, however, can preserve radioactive elements whose predictable decay acts as a geological clock. Radiometric dating uses that natural clock to determine when a rock crystallized. If samples from Jezero eventually reach laboratories on Earth, scientists could measure those isotopic systems with instruments far more precise than anything a rover can carry. Several samples collected by Perseverance contain igneous material. They have been sealed and placed in carefully selected locations on the Martian surface, creating a geological archive that can potentially be studied in greater detail later. Their mineral grains may preserve chemical information that the rover cannot fully decode in place. For you, the significance reaches beyond one crater. Jezero is a place where two major chapters of Martian history overlap. The rocks preserve volcanic activity, while the overlying landscape records the later influence of flowing water. That combination gives scientists something rare, a chance to establish when the volcanic foundation formed. Then compare that age with evidence for ancient water activity. A single piece of Martian rock could eventually connect those events across immense spans of time. The rover's discovery, therefore, adds depth to Jezero's story. Beneath the traces left by an ancient river, Mars still carries the hardened remains of molten rock that came before it. If we want to witness a volcanic world in motion, Io gives us the closest natural comparison. The innermost large moon of Jupiter remains the most volcanically active body known in the solar system, with eruptions occurring across a landscape continually reshaped by molten rock. Its surface carries sulfur and sulfur dioxide deposits in yellow, orange, red, and white. Beneath those colors, hundreds of volcanic centers release lava and towering plumes into an atmosphere too thin to contain them, like Earth's atmosphere does. At Loki Patera, an enormous lava lake stretches roughly 126 miles across. Periodically, its surface overturns as fresh, molten material advances across the lake, replacing older crust with a new layer. The source of Io's heat is unusual. Radioactive decay contributes some internal energy, but tidal heating dominates. Jupiter's immense gravity repeatedly stretches and compresses Io during its orbit, flexing the moon's interior and converting mechanical energy into heat. That process keeps portions of Io's interior molten. The result is a world where volcanic activity operates on a scale we can observe from orbit, sometimes producing plumes that rise hundreds of miles above the surface. For comparison, Mars has no nearby giant planet continually squeezing it through gravitational tides. Its ancient volcanic energy came from its own interior, where heat left from planetary formation and radioactive elements powered melting and magma movement over immense spans of time. The difference in mechanism matters. Io is being actively heated today, while Mars gradually lost the internal energy that once drove its greatest volcanic systems. Yet the landscapes left behind tell us that ancient Mars could sustain prolonged volcanic activity across enormous regions. Imagine the Tharsis province during its most active periods. Magma would have risen through fractures, lava would have spread across the surface, and enormous volcanic structures would have grown through repeated eruptions. New flows would have buried older ones, while gases entered the atmosphere above them. We cannot watch that ancient Mars directly. Instead, we reconstruct its activity from mineral deposits, lava boundaries, collapsed chambers, volcanic vents, and the ages of surfaces preserved across the planet. Io gives those clues a living counterpart. Its lava lakes show how molten rock can reshape a surface repeatedly. Its eruption plumes demonstrate how volcanic gases and debris behave under extremely thin atmospheric conditions. Mars once possessed a warmer interior and a much more vigorous volcanic system. Its eruptions eventually became less frequent as internal heat declined, leaving behind structures whose enormous dimensions preserve that earlier energy. Standing between these two worlds, we can see the contrast clearly. Io remains powered from within today, while Mars carries the geological remains of a far more active age. The rust-colored surface we observe now is only the latest layer. Beneath it lies a planet whose interior once drove immense rivers of molten rock across an entire world. Venus offers us a useful mirror for understanding Mars, because beneath their very different appearances, both worlds share a similar volcanic inheritance. Earth, Venus, and Mars formed from the same early solar system, yet their interiors followed different paths as their heat slowly escaped into space. The resemblance becomes striking when we examine Venus more closely. The planet is almost the same size as Earth, with a similar density and substantial internal heat, but its surface is dominated by volcanic structures, rather than moving tectonic plates. Between 1990 and 1994, the Magellan spacecraft mapped Venus using radar. Its observations revealed vast lava plains, shield volcanoes, volcanic domes, and thousands of smaller volcanic structures scattered across the surface. Among the most distinctive are coronae, enormous circular features created by deformation and volcanic activity around rising or sinking material beneath the crust. Some stretch for hundreds of miles, revealing how deeply Venus has been shaped by processes within its interior. Mars followed a related path. Without Earth's moving tectonic plates, its largest volcanic centers remained fixed over their sources for immense periods, allowing repeated eruptions to build enormous structures in place. Venus shows us what that planetary arrangement can produce. Instead of distributing volcanic activity across shifting boundaries, heat can remain concentrated beneath particular regions, feeding enormous provinces until the interior gradually loses enough energy to reduce the activity. Then came a remarkable discovery. In 2023, researchers re examined radar observations from Magellan and found a volcanic vent whose shape appeared to change between two observations separated by 8 months. The alteration was consistent with either an eruption or a collapse event. If volcanic activity caused the change, Magellan had effectively captured evidence of a geological event occurring during its mission. That matters for Mars because direct observations of eruptions are almost impossible there. We depend largely on surface ages, mineral evidence, seismic measurements, and structures preserved across geological time. Venus gives us another piece of the puzzle. It demonstrates that a rocky planet can retain substantial volcanic activity long after its surface becomes fundamentally different from Earth's. There is something else worth noticing. Venus and Mars are both worlds where volcanism helped shape the surface without the constant recycling created by Earth's plate tectonics. Their volcanoes could grow enormous. Their lava fields could remain preserved. Their crust could hold geological memories for billions of years. Io presents one extreme, with tidal forces continually supplying heat. Earth occupies another position, with active volcanism intertwined with moving plates. Venus and Mars occupy later stages, where internal heat remains but its expression becomes increasingly localized and intermittent. For you, the night sky may make these planets appear like simple points of light. Their surfaces tell a different story. Beneath those distant worlds, heat has been moving for billions of years. Rock has melted, risen, spread, hardened, fractured, and sometimes melted again. Mars belongs to that larger family of changing rocky worlds. Its volcanoes are not strange exceptions. They are part of a planetary cycle in which internal heat slowly writes itself onto the surface, one eruption at a time. The next answers about Martian volcanoes may come from places we cannot reach with cameras alone. Some questions require instruments beneath the surface, laboratories on Earth, and eventually people standing on Mars. Perseverance has already changed what we can learn from Jezero Crater. Since landing in 2021, the rover has collected carefully selected cores and sealed them inside sample tubes. Several contain igneous material, preserving evidence of the volcanic foundation beneath the crater. Their value goes beyond simply examining another Martian rock. On Earth, laboratories can measure radioactive isotopes with extraordinary precision, allowing scientists to determine when a mineral crystallized. A returned Martian sample could therefore provide an age far more precise than estimates based only on crater counting. But the return of those samples is still a developing international effort. NASA and the European Space Agency are studying alternative architectures for bringing Perseverance's collection back to Earth, with a final approach expected to be selected after further evaluation. If those rocks eventually reach terrestrial laboratories, we could establish when Jezero's volcanic basement formed, how its minerals crystallized, and how volcanic activity overlapped with ancient water. Another missing piece lies beneath the surface. Insight proved that Mars can reveal its interior through seismic waves, but one lander could only sample a limited region. A future network of seismometers spread across Mars could locate smaller Marsquakes, trace their paths, and distinguish deep tectonic stresses from possible movement of magma. That distinction matters. A detected seismic source beneath a volcanic province would tell us whether heat remains capable of moving molten material through the crust, even if no eruption has occurred for thousands of years. There are also mission concepts designed around the intersection of heat, water, and chemistry. Mars Life Explorer, studied as part of planetary science planning, was designed to investigate the shallow subsurface, including ice and the chemical conditions that could preserve evidence of past habitability. Volcanic regions could become important targets because hydrothermal systems combine several ingredients that matter to planetary scientists. Heat provides energy. Circulating fluids transport chemicals, and mineral surfaces can preserve traces of ancient reactions. Human exploration would add an entirely different capability. Astronauts could examine outcrops directly, deploy instruments across broad areas, and enter natural volcanic structures, such as lava tubes where appropriate. Those tubes could provide potential shelter from radiation while also preserving geological records beneath the exposed surface. Their usefulness would depend on their stability, accessibility, and exact local conditions. The future of Martian volcanology therefore extends beyond counting craters or photographing ancient lava. It could involve laboratory measurements, seismic networks, subsurface investigations, robotic exploration, and eventually human fieldwork. Each method answers a different part of the same problem. How long did Mars remain internally active? Where did that heat persist? And how did it shape the environments around it? For you, the most important change may be simple. Mars is becoming a place we can investigate directly, layer by layer, sample by sample, with increasingly precise tools. Mars asks us to abandon the clock we carry in our heads. Its volcanic history stretches across roughly 3.5 billion years, a span so large that ordinary human experience cannot provide a useful comparison. Imagine compressing that history into one day. Most of the events we know from human civilization would disappear into a fraction of a second. Even the rise of complex life on Earth would occupy only a small portion of the final hours. Volcanic activity on Mars endured across much of that immense interval. It was measured through countless episodes, separated by long pauses, with lava accumulating in layers that gradually altered entire regions. Olympus Mons makes this scale easier to see. Its immense structure was assembled through repeated eruptions rather than one overwhelming event. Each flow added another layer, sometimes only a modest thickness, while older surfaces cooled and hardened beneath it. Then the process repeated, again and again. For a single eruption, the landscape might have changed only slightly. Across millions of years, those small changes accumulated into a mountain larger than anything Earth has produced. You can stand beside an ordinary lava field and understand its dimensions. Geological time is different. We have no instinct for watching a surface change over 10 million years, or for imagining another 100 million years passing without the basic process stopping. That is why Martian volcanoes can seem almost impossible when viewed in a single image. A photograph captures one moment, while the structure itself represents an accumulation of events separated by spans longer than the entire existence of our species. Consider human history for a moment. Written records cover only a tiny fraction of our past. Cities rise and disappear, languages change, and generations replace one another. Mars was already building volcanic landscapes before any of those cycles began. The same perspective changes how we interpret an apparently simple lava flow. A dark surface may represent one eruption or several episodes that spread across the same region at different times. Craters, fractures, and overlapping boundaries become markers in a geological record measured across immense intervals. Nothing about the process required a single dramatic moment. Its power came from repetition. That principle reaches beyond Olympus Mons. The great volcanic provinces of Mars were constructed through persistent internal heat, acting over extraordinary durations. Their final shapes are therefore records of time as much as records of eruption. When you look at Mars, you are seeing the result of processes that operated far beyond the scale of a human lifetime. The planet does not need to change quickly to be active in geological terms. It only needs to keep changing. And given enough time, even small additions become mountains. Mars gives us something rare in planetary science, a world caught between geological eras. Its rocks preserve a long record of cooling, crustal change, volcanic construction, and interior evolution. When we compare that record with Earth and Mercury, a broader pattern begins to emerge. A rocky planet starts with immense internal heat. Some comes from its formation, when countless bodies collided and merged. More remains through the radioactive decay of elements buried deep inside the planet. That heat drives movement within the interior, shaping the surface from below. Earth still has abundant internal energy. Its liquid outer core sustains a global magnetic field, while heat escaping from the interior helps power mantle convection and plate tectonics. Volcanoes continue to build new land, and earthquakes constantly rearrange the crust. Mars occupies a different stage. Its crust no longer participates in global plate tectonics, and its volcanic activity has diminished dramatically. Yet the planet still releases measurable internal heat, and seismic activity shows that its interior has not completely stopped moving. Then there is Mercury, much smaller than either Earth or Mars. Its interior cooled faster, leaving a world where large-scale geological activity has become extremely limited. Its surface preserves ancient terrain across immense stretches of time, interrupted mainly by impacts and smaller changes. Seen together, these planets form a useful sequence. Earth represents a relatively energetic present, Mars preserves a later stage, and Mercury shows what prolonged cooling can eventually produce. But planetary aging is not perfectly synchronized. Size matters, composition matters, and the amount of heat retained inside each world changes the pace. A larger planet generally holds internal heat longer, while a smaller one loses it more efficiently. That difference helps explain why planetary landscapes can preserve history for so long. That difference helps explain why Mars can retain evidence of ancient volcanic systems long after their major activity faded. The planet became less capable of renewing its surface, allowing older structures to remain exposed for extraordinarily long periods. You can think of planetary evolution as a gradual redistribution of heat. Deep inside, energy moves outward. At the surface, that energy appears as volcanism, tectonic movement, and other geological processes. As the interior cools, those processes become less frequent. Earth is still somewhere within that long progression. Its future lies far beyond any human timescale, but its interior will eventually lose much of its present energy. Mars, therefore, becomes more than an archaeological site. It becomes a reference point for understanding planetary aging, showing us what a cooling, rocky world can preserve when its interior begins to lose the power to reshape the surface. The landscape records that transition. Every ancient volcano, hardened lava field, and surviving fracture carries evidence of a planet gradually changing from active to enduring. Olympus Mons remains beyond the reach of every human footprint yet placed on Mars. We know its shape from orbit. We know its history through patterns preserved across the surrounding terrain. Even so, the volcano itself remains almost entirely untouched by direct exploration. No astronaut has stood on its slopes. No rover has crossed its lava fields. Every detail has reached us through spacecraft, orbital cameras, radar measurements, and instruments examining Mars from above. That distance creates an unusual kind of knowledge. We can measure the volcano with remarkable precision while never standing beneath its summit. We can trace ancient lava boundaries across hundreds of miles, identify collapsed structures, and reconstruct changes that unfolded over hundreds of millions of years. Yet the actual rocks remain where they formed. The summit caldera is especially important. 6 overlapping collapse structures record separate episodes in the volcano's eruptive history, each preserving evidence of changes beneath the surface. From orbit, we can map their outlines and fractures, but we cannot yet examine those walls at ground level. The same limitation applies to the enormous escarpment surrounding Olympus Mons. Its exposed layers preserve successive volcanic deposits, allowing scientists to reconstruct how the mountain grew through repeated eruptions. Still, no instrument has drilled into those layers there, and no sample from the escarpment has been returned to Earth. Imagine walking across that terrain. You would encounter rocks formed during different stages of Martian volcanic history, separated by distances that could take days or weeks to cross. Some surfaces would preserve textures created by flowing lava, while others would record fractures, collapses, and later geological changes. Every step could cross another chapter. Above you, the summit would rise far beyond ordinary terrestrial mountain scales. The surrounding landscape would extend toward the horizon, shaped by a volcano whose construction occurred through countless individual events rather than one enormous eruption. What would a human explorer actually find there? That remains unknown. We have never examined an Olympus Mons lava flow with the kind of detail possible from the ground. We have never held a rock from its flanks, measured its texture by hand, or watched its geological layers pass beside a rover's cameras. Even the dust surrounding the volcano carries information about its surface chemistry and atmospheric environment, but orbital observations cannot replace direct investigation. There is also something remarkable about the age of this landscape. Mars has preserved volcanic structures for immense spans of time because erosion and tectonic recycling operate far more slowly there than on Earth. The mountain remains, its history remains, and the unanswered details remain with it. Olympus Mons is therefore more than a monument to ancient volcanism. It is one of the largest places in the solar system that humanity has studied extensively without ever reaching the ground beneath its feet. We have mapped it, measured it, photographed it, and reconstructed parts of its history. But the mountain itself has never met us. Mars offers one of its strongest clues to past habitability beneath the surface, where volcanic heat once met flowing water. On Earth, that meeting creates hydrothermal systems, environments where heated water moves through fractured rock and gathers dissolved minerals, Some of the most unusual ecosystems on our planet depend on these systems. At deep ocean vents, microorganisms obtain energy from chemical reactions rather than sunlight, forming the foundation of communities far below the reach of daylight. Early Mars possessed ingredients for similar environments. Active volcanism supplied heat, while ancient rivers, lakes, and groundwater provided water that could circulate through fractured crust. Where those fluids encountered hot rock, chemical gradients would have developed naturally. Those gradients matter. Life requires usable energy and accessible chemistry. Hydrothermal environments can provide both at the same location, allowing water, minerals, and heat to interact continuously. On Mars, volcanic regions could therefore have created localized habitats even while the planet around them was becoming increasingly cold and dry. The Tharsis region is especially important because its enormous volcanic systems remained active across immense stretches of geological time. Their heat would have affected surrounding groundwater, while fractures in the crust created pathways through which fluids could travel. Beneath the surface, these interactions could have persisted long after conditions at ground level became hostile. But habitability alone does not establish life. Scientists still need evidence that Martian environments crossed the much harder boundary between chemistry and biology. Organic molecules have been detected on Mars, and minerals associated with ancient water have been identified, but neither observation proves that living organisms ever existed. The deeper question concerns duration. A brief hydrothermal episode might create interesting chemistry, while a system maintained for thousands or millions of years could provide far more opportunities for complex reactions to accumulate and repeat. We cannot watch those ancient systems operating today. Instead, we search for their geological fingerprints. Rocks can preserve mineral changes caused by heated fluids. Certain chemical patterns can reveal prolonged interaction between water and volcanic material. Fractures can mark pathways that once carried underground fluids through the crust. That makes volcanic terrain valuable for astrobiology. The rocks themselves become records of where heat and water once met. If life ever emerged on Mars, the surface may be the least promising place to find its remnants. Ultraviolet radiation and the harsh environment have altered exposed material for immense spans of time, while the subsurface offers greater protection and potentially more stable conditions. Deep underground, isolated pockets of water could still exist where geothermal heat remains. Whether any such environments actually persist is unknown, but the possibility gives Martian volcanism a second significance. The volcanoes may have shaped more than the landscape. They may have created some of the environments where chemistry had its opportunity to become biology. And if that transition ever happened, the evidence may still be hidden inside the rocks. Mars leaves behind a strange inheritance. Its volcanoes transformed the planet over immense stretches of time, building mountains, altering the crust, influencing the atmosphere, and creating pathways through which heat and water once moved beneath the surface. Much of that activity ended long ago, yet its consequences remain written across the landscape. The legacy is visible from orbit, but it may become even more important from the ground. Future explorers could cross lava plains where ancient flows hardened into rock. They could enter lava tubes formed when molten material drained away, leaving passages beneath the surface. Those spaces could provide natural shelter from radiation and extreme surface conditions, turning ancient volcanic structures into practical environments for human exploration. A settlement on Mars would therefore exist inside geological history. Its foundations might rest on rock created by eruptions, millions or billions of years before humans arrived. Instruments could examine mineral layers, fracture systems, and buried volcanic deposits, gradually reconstructing how the planet changed from a warmer, more active world into the colder landscape we see today. The deeper story may lie below. Where volcanic heat once encountered groundwater, chemical reactions could have altered surrounding minerals and created environments suitable for microbial life. If organisms ever occupied those systems, traces of their existence might remain protected underground, preserved within minerals, or enclosed inside ancient rock. Finding such evidence would change the meaning of Mars. A microscopic fossil, a distinctive chemical pattern, or another convincing biosignature could establish that life emerged beyond Earth. It would also connect two very different chapters of planetary history, one written in volcanic heat and another in biological activity. We do not know whether that connection exists. That uncertainty is part of what makes Mars so valuable. The planet preserves ancient environments that Earth has largely erased through erosion, tectonic recycling, and continual geological renewal. On Earth, old surfaces disappear. On Mars, they can remain. That preservation gives us an unusual opportunity. We can study a world whose geological record reaches deep into the past, then compare its history with our own planet's continuing evolution. The volcanoes are central to that record. They built enormous regions of crust, redirected water, modified atmospheric conditions, and created underground structures that could someday support exploration. Long after the eruptions ended, their architecture remained. Perhaps that is the most enduring legacy of Martian volcanism. Fire created the landscape, water transformed parts of it, and time preserved the evidence. Now we are learning how to read it. Mars may never speak in the way another living world could. Its answer, if one exists, will come through rock, chemistry, minerals, and carefully gathered samples. And when we finally understand those records, we may discover that the volcanoes were more than builders of a planet. They may have built the places where its deepest question was preserved.